Now let's talk about queues. So a queue has some similarity with stack, but it's in a fundamental way different. So it's an abstract data type, and these are the operations that it has. You can enqueue a key, and it adds the key to the collection. And then when you dequeue, that gives you back a key and removes it from the queue. It removes and returns the least recently added key, rather than, in the case of a stack, the most recently added key. So that's the fundamental difference. If you think about queues as like queuing up in line or waiting in line, this is a first come, first serve situation. So the longer you've been waiting in line, so the longest person waiting in line is the next person to be served. Does that make sense? So you can imagine if you had a grocery store that had a stack that it used for serving people, people would be pretty annoyed, right? Because the person who just arrived, you've been waiting in line 10 minutes, a person just arrives, they get served before you do. That would not make you happy. So queues are very useful, for instance, for things like servers, okay, where you've got a bunch of operations coming in and you want to service the one that's been waiting the longest. The other operation is you can find out whether a queue is empty or not. Okay? So these are often called FIFO, first in, first out, and this distinguishes them from stacks, which are LIFO, last in, first out. Okay? First in, first out, or first come, first serve. Same thing. How can you implement a queue? Well, one way is with a linked list, where you have a head and a tail pointer. So let's say we start out with an empty linked list. We can go ahead and enqueue, and what we're going to do basically in an enqueue is we are going to push to the back of the linked list. So that's how we'll implement enqueue. So here we enqueue A, it's now at the back of the linked list. If we enqueue B, it's going to be then added again at the end of the linked list. Is it empty? No. How do we know it's not empty? Well, the simplest thing is we would just call to the underlying list implementation and say, hey list, are you empty? It would say no. And so empty for the queue is no. We know it's really happening just by checking whether the head is nil or not. If we enqueue C then, again it goes to the tail of the list. And if I now dequeue, which one is going to be removed? Again, this is not a stack. In a stack, C would be removed. In our case, A is going to be removed because it's been there longest. That's just an implementation of popping from the front. Okay. So that would return A. We can now do some more enqueuing, enqueue D, enqueue E, enqueue F. And now if we start dequeuing, we dequeue from the front. So dequeuing B, dequeuing C, dequeuing D, dequeuing E, and finally dequeuing F. If we ask whether the queue is empty now, the answer is yes. Again, because the head is nil. So enqueue uses list's pushback call, and dequeue uses both the list's top front to get the front element, as well as pop front to remove that front element. And empty just uses the list's empty method. What about with an array? We could think of doing something similar. That is, we could add at the end and then pop from the front. But you can imagine, so we said basically if we said the front of the array is the beginning of the queue, then enqueuing is easy, but dequeuing would be an expensive order in operation. And we want enqueuing to be order 1. We can do that in a fashion I'll show you right now, which is basically keeping track of sort of the array as a circular array. So we're going to go ahead and enqueue A, and we have a write index. So the write index tells us where the next enqueue operation should happen. And the read tells us where the next dequeue operation should happen. So we enqueue A, we enqueue B, and now update our write index. If we ask whether we're empty, no, we're not empty because read is not equal to write. That is, we have something to dequeue that has been enqueued. Okay. So empty would be false. We enqueue C. If we dequeue, again, we're going to dequeue A, so we dequeue from the read index. So we basically read what's at the read index and then increment the read index. If we now dequeue again, we read what's at the read index, which is B, and we increment the read index. Now we'll do some more enqueuing. Notice at this point when we enqueue D, the write index is 4. That's the next place we're going to enqueue to. So we enqueue E, which will have us write to the index 4, and then the write index wraps back around to the initial element. And here it's important to note we're using zero-based indexing of this array, right, because of the fact that the first element is 0. We enqueue again, enqueue F, and now if we try and enqueue G, it's not going to allow us to do that. So that will be an error. The reason it would be an error is if we did enqueue G, the read and the write index would both be 2. And it would be hard to distinguish read and write index to 2 because the queue is full, or read and write index both 2 because the queue is empty. So therefore, we have a buffer of at least one element that can't be written to, okay, to make sure read and write are separate and distinct if the queue is not empty. Now we'll dequeue, so we'll dequeue C, basically reading from the read index and updating it, dequeue D, read from the read index and update it, dequeue E, and here again the read index wraps around back to 0. And now finally we do our final dequeue, and now the read and write index are both 1, which means if we ask whether the queue is empty, the answer is yes, it is empty. So what we see here is that the cost for doing a dequeue and an enqueue, as well of course as empty, are all order 1 operations with this array. So we can use either a linked list, although we have to have a tail pointer so that pushback is cheap, or an array. Each of the operations is order 1. One distinction between the array and the linked list implementation is that in the array implementation, we have a maximum size that the queue can grow to, so it's bounded. Okay? Maybe you want that, in which case it's fine, but if you don't know a priori how long the queue you need is going to be, an array is a bad choice. And any amount that is unused is wasted space. In a queue that's implemented with a linked list, it can get arbitrarily large as long as there's available memory. The downside is every element you have to pay for another pointer.